We are interrupting eigenvalues for a quick polynomial review. Not ring theory. Just enough algebra to keep the next proofs from collapsing into fog. A polynomial is a finite sum of powers of the variable, with coefficients from a field f. For us, f is either the real numbers or the complex numbers. The largest power with non-zero coefficient is the degree. Finite sum is important. Infinite sums are a different zoo. And this zoo is already loud enough. Why are we doing this in the middle of eigenvectors? Because soon we will plug a linear operator into a polynomial. If T maps a vector space to itself, then T squared, T cubed, and P of T makes sense. This is where polynomials become linear algebra weapons. Because apparently matrices needed accessories. We only care about two cases right now: polynomials with real coefficients, and polynomials with complex coefficients. The difference matters. The real polynomial x squared plus 1 has no real root, but over the complex numbers it splits into x minus I times x plus I. The fundamental theorem of algebra says every non-constant complex polynomial has at least one complex root. We are not proving it here. It is an existence theorem, and its proof belongs to analysis. Linear algebra will simply borrow it and act innocent. For real coefficients, non-real complex roots appear with their complex conjugates. If a plus bi is a root, then a minus bi is also a root. The reason is simple. Conjugating an equation with real coefficients preserves the equation. The pair multiplies into a quadratic with real coefficients. The fundamental theorem of algebra implies every non-constant complex polynomial factors into degree 1 pieces. Find one root. Peel off one factor. Repeat. Eventually the polynomial is completely split. It is algebraic meal prep, but with more symbols and less nutrition. Over the real numbers, non-constant polynomials factor into degree 1 and degree 2 pieces. The degree 2 pieces come from conjugate complex pairs. You multiply the pair together, and the imaginary parts cancel. Finally, the symbols do something considerate. That is the minimum polynomial toolkit. Definition: real versus complex coefficients, the fundamental theorem of algebra, conjugate root pairs, and factorization. Next, we use this to prove that every operator on a finite-dimensional complex vector space has an eigenvalue. The plot has finally remembered where it was going.